Okay, well, I see from the online chat room that you seem to have got the idea between the distinction between a solute, which is an electrolyte in aqueous solution, and solutes, which are non-electrolytes. And I foreshadowed, just at the end of that last discussion, the distinction between strong electrolytes, which are strong electrolytes. Let me start again. Solutes, which are strong electrolytes, and solutes, which are weak electrolytes, all in distinction furthermore from non-electrolytes. There was also a lot of discussion and obviously a bit of awe and wonder about the demonstration I did, so by public demand I will quickly run through that demonstration again. I've got a low voltage DC electric potential going across here, and I've got deionized pure water there, and my light doesn't come on, so there is no conduction of electricity as you'd expect with pure water. If I put some ethanol into this solution and stir it up, the light remains off. The solution does not conduct electricity, so ethanol is a non-electrolyte solute. Remember, the term electrolyte or non-electrolyte is talking about solutes, the stuff that we dissolve, not the solution. Now if I add some acetic acid or ethanoic acid to this, put that top on quickly and stir it up. Don't know if you can see that very well, but I hope that you can see that the light has come on. It's not very bright, but it's come on. So the solution is conducting electricity, so acetic acid, the solute, is an electrolyte. Now I'll add a solution to which the solute hydrogen chloride gas has been dissolved. That's called hydrochloric acid solution. I've got a solution of that already, so I'll just put some of that in here. And no question, this conducts electricity, so hydrogen chloride gas is an electrolyte solute. And you can see now this bright is this light is very, very bright. Okay, so let me just get that out of the way for now. Aussie, why was the light so much less bright when acetic acid was added to the water compared with when hydrogen chloride was added to the water? That in fact is the question that is the issue of this whole little session. So let's think about that. What can we deduce? Seems pretty obvious that electricity is able to be conducted better through that system with the hydrogen chloride dissolved than with acetic acid dissolved. We have a picture that electricity in solution is carried by charged ions. So would it make sense if I suggest to you that in the hydrochloric acid solution, the solution containing hydrogen chloride solute, there are more ions than in the solution containing the acetic acid solute? Now I'm going to suggest to you, and you're going to have to accept, I guess, that in the case of hydrogen chloride, if I put that into water, dissolve some gas, all of it ionizes. So all of it goes to, in the presence of water, hydrogen ions and chloride ions. And we believe that to happen, that the interaction of water molecules around every molecule of HCl, they're pulling away. Chloride has a partial negative charge, hydrogen partial positive charge. The interaction is such that these are pulled apart. This happens to the point where the concentration of hydrogen chloride is 0 in solution. In a solution of hydrogen chloride, there is no hydrogen chloride. It's the same as in a solution of sodium chloride, there is no sodium chloride. In this case, there's no hydrogen chloride, there are only hydrogen ions and chloride ions. This then is called a strong electrolyte. This is the word that we use to describe this sort of thing. Now, just by the by, there's another way that we can represent this process. And that is to show that water is not just something in which this happens, but that water is a reactant, a chemical reactant with the hydrogen chloride. Another way of representing this is that the hydrogen chloride reacts with water molecules. Each molecule reacts with water molecules, and we represent this, which is a hydrogen ion surrounded by water molecules. Another way to indicate that is that there's actually a hydrogen ion attached to a water molecule. It's a simplified representation of lots of water molecules attached to a hydrogen ion. This is called a hydronium ion. That's the term we use for that representation. Okay, that's a strong acid. Now in the case of acetic acid, the light didn't come on nearly as brightly as with the hydrogen chloride. And we can make the deduction that there are less ions in the acetic acid solution. So how do we get there? We can perhaps draw the conclusion that in the case of acetic acid, only some of the molecules of the solute ionize. So now I'm going to suggest that in the case of acetic acid, and here's the bond that we're talking about breaking in the case of, well, I'll write it with H2O. Only some of these form ions, and H3O plus. And why do that only some of these? I'll say some ionize is the word. They're all symbols, they've got meanings, is the word for when that bond breaks, when waters interact around that. And if only some do, this is what we call a weak electrolyte. And the explanation of why some do is that this system reaches a condition of dynamic chemical equilibrium. We've struck that in several other instances where I now want to change this symbol to the double arrow, meaning that when some of this ionizes, the concentrations of these species come to a point where the reaction that way is happening equally fast with the reverse reaction that way. So the concentration of this stays the same, concentrations of these stays the same. Not because nothing's happening, but because it's going that way just as fast as this way. Okay? And so the distinction between a strong electrolyte solute and a weak electrolyte solute is to do with how much of it ionizes. In the case of a strong acid, all of the solute ionizes. I'm particularly using acids as my examples of strong electrolytes and weak electrolytes, but there are other sorts. I'm just focusing in on those. And weak electrolytes, only some of the solute molecules ionize that it reaches a point of equilibrium? Jacinta. How many ionize? Wonderful question. What we can talk about where I'm going. So I love the question. What is the fraction of the weak electrolyte solute that ionizes? Now, this is different from solute to solute to solute. So every weak solute ionizes incompletely and to a different extent, more so or less so. And I happen to have prepared, which could be seen as an answer to your question, Jacinta, but I had already contemplated this, that here are, it changes a bit with temperature and it changes a bit with the concentration of the solute. So I'm going to eradicate those variabilities. All these solutions of all these solutes, dichloroacetic acid, hydrogen fluoride, acetic acid, hypochlorous acid and hydrogen cyanide, all, if they are all 0.1 molar solutions in water and all at 20 degrees, then there are ways of estimating how much ionizes. One way is by measuring the amount of current, because the amount of the ability to conduct electricity depends upon how many what the concentration of ions are. That's one way. Another way is that there are many solutions. There are many properties that depend upon the concentration of ions in a solution. So by measuring how far melting point of a solution goes down or boiling point goes up, we can estimate the concentration of ions in a solution. You have to take my word for it that these are estimates of how much these species ionize. So in the case of dichloroacetic acid, 50% is ionized and 50% remains as the solute molecules, about half and half, when it reaches a condition of dynamic chemical equilibrium. In the case of hydrogen fluoride, less, about 8% ionizes and 92% remains. In the case of acetic acid, only about 1%, a little bit more, and 98.7% remains as acetic acid molecules. Hypochlorous acid, only 0.5% and 99.5% remains. Come down to hydrogen cyanide, very, very little ionizes, a little bit less than 0.01% and 99.9% remains as the molecules of the solute. So can you see that, for example, in a solution of HF, 0.1 molar, then this 92% remaining behind will be 0.092 molar. This is 92% of that concentration remains there. And the concentration of hydrogen ions is 0.008 molar, using a big M for moles per litre. And I hope you can see also, if the concentration of fluoride ions is 0.008 molar, the concentration of hydrogen ions will also be 0.008 molar, because all of these chemical reactions, as shown by the equations, produces an equal concentration, or equal number, if you like, of those and those. Okay? Now, these are all weak electrolytes. And weakness, a strong one is one in which all of the molecules would ionize. This one's only got 50%. This one, 0.01%. Can you accept that in terms of degrees of strength and weakness? These ones going up this way are stronger, 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 stronger. And going down this way, weaker, 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 weaker. So, for example, HF ionizes more than hypochlorous acid, we say that this is a stronger weak acid than this is. Okay? So weak acids can vary in their strength or their weakness. Dichloroacetic acid is a strongish weak acid, weak electrolyte, and also weak acid. But hydrogen cyanide is very, very weak electrolyte. Okay? Victor? Oh, wonderful. Victor is now relating what we've talked about here back to the demonstration that I showed you. And you're suggesting that if we'd done that twice, once with dichloroacetic acid and once with hypochlorous acid, that the light would have shone more brightly in this solution than in that solution because there are more ions. Excellent. Yeah. All right, just a little warning. The word strong has a particular meaning. So much of chemistry is, for communication purposes, needs very particular use of terms. And the word strong in this context applies to whether any of the molecules of solute ionize when we put them into water or whether they don't. That's a strong one. Sorry, it's a weak one. And there are degrees of strongness. Sometimes, and in particular, people talk about a strong acid solution when they mean it's very concentrated. It's bad use of the terminology strong, but not to be confused with the property of the solute about whether it electrolyzes or not. Okay, our next session I'll take you through a little bit where these figures have come from, a little bit of mathematical quantitative discussion of these weak electrolytes.